Let's look at question number 1. Question number 1 says, in a steam boiler, hot gas or hot gases transfer heat to water which vaporizes at a constant temperature. In a certain case, the gases are cooled from 1100 degrees Celsius to 550 degrees Celsius, while water vaporizes at 220 degrees Celsius. The specific heat capacity of the gases is 1.005 kilojoule kg per Kelvin, and the latent heat of water at 220 degrees Celsius is 1858.5 kilojoule per kg, because it vaporizes at a constant temperature. So the case would be of a latent heat absorption. So all the heat that is transferred from the gases goes into the water. How much entropy increase is there due to the irreversible heat transfer, that is the heat transfer through a finite temperature difference? If the surrounding temperature is 30 degrees Celsius, now this is nothing but your T naught, find the increase in the unavailable energy due to the irreversible heat transfer. Now, in this particular question, let us take a look at this particular diagram given to us. Now, in this diagram, what is happening? Let us say the mass flow rate of gases is m dot g. So this is the mass flow of the hot gases. Alright. Now I don't have the mass flow rate of water. So let us say the mass flow rate of water is 1 kg per second. So let's find out all the values for 1 kg of water evaporated. Okay. So let us say that the gases which are of mass mg dot, they are cooled from 1100 degrees Celsius to 550 degrees Celsius. So let us say from state 1 it cools down to state 2. So this is the direction of the cooling of the gases from 1 to state 2. Okay. Now for a reversible heat transfer, the working fluid in the heat engine having the same Cp would have been heated along to 1. So this path is for the reversible heat addition in the working fluid, so that the temperature difference between the gases and the working fluid is 0 at all times. Okay. Now, if you look at the path 1b, so path 1b, so this path illustrates or denotes the expansion of the working fluid down to the lowest possible temperature, that is the surrounding temperature. So 1b is the expansion of the working fluid to T naught. Okay, and the amount of heat that is rejected in this particular case during the expansion is given by the area ABCD. So this is the area which gives the amount of heat that is rejected. Okay, so let's write it down. So area ABCD, this gives the amount of heat that is rejected. Alright, now when the water evaporates at 220 degrees Celsius, okay, so water evaporates at 220 degrees Celsius, the gases gets cooled from 1100 to 550 degrees Celsius. Okay, and the resulting power cycle has an unavailable energy which is represented by the area AEFD. So if you look at this area, that is, if I make it in red stripes, so this complete area is the unavailable energy for the given power cycle. Okay, so this is how the whole process is going on. Alright, so if you now talk about the increase in the unavailable energy due to the irreversible heat transfer, it is given by the area BEFC. So this area gives the, so let me write it down again. So the area AEFD, this area gives the unavailable energy for the whole power cycle. So this gives the unavailable energy for the complete power cycle. Alright, and if you just take the area, which is BEFC, so area BEFC, this is the unavailable energy due to the irreversible heat transfer. So this is unavailable energy for, or you can say due to, the irreversible heat transfer. Alright, so let's go to the first part of the question that says, what is the entropy increase due to the irreversible heat transfer? So let's find it out. So let us give it the part A of the question. So the entropy increase of water. So entropy increase of water, this is equal to the amount of heat that is absorbed, and that amount of heat is the latent heat that is absorbed. Latent heat absorbed upon the temperature at which the water boils. So this is 1858.5 upon the temperature is 220. 220 degrees Celsius plus 273, it makes Kelvin out of it. So the value would become 3.77 kilojoule per kg Kelvin. So this is the entropy increase of, let us say, 1 kg of water. Okay. Now, if you look at the next part, it says that what is the increase in unavailable energy due to the irreversible heat transfer. Okay. So the increase in the unavailable energy, let's give it part B. So the increase in unavailable energy, this is given by T naught into delta S total. Alright, and delta S total, if you have to find out this particular value, this is nothing but delta S for water plus the delta S for gas. So now we have the value for delta S for water. We have to find out the value for delta S for the gases. Alright, now the delta S for the gases, so let's find it out. Delta S for the gas, this is equal to, from the gas temperature 1 to gas temperature 2, this is dq upon T. Now the amount of heat that is lost by the gas is mCp delta T, isn't it? So this is mg dot into Cp of the gas into dt upon T. So let's go back to the question. It says the specific heat capacity of the gases is how much? 1.005 kilojoule per kg Kelvin. But I am not sure about the amount of mass flow rate in the case of the gases. So how do I find out this particular quantity? Now there's one thing that is there, that is whatever heat that is transferred from the gas, it is absorbed by the water. Okay, so you can say, so this is the heat that is lost by the gas. Okay, lost by the gas. All right, so the amount of heat lost by the gas, this is equal to heat gained by the water and that is the latent heat. So let us say that is the 1 kg of water that is absorbing the heat, so it becomes equal to 1 kg into 1858.5. so this is the amount of heat that is gained by the water or lost by the gases. So this can be put equal to mg dot into cpg, and the dt is 1100 minus 550. Alright, so if you bring this particular term in the denominator, you will get the value for mg into cpg. So this becomes mg dot, or you can say just mg into cpg. This is equal to 1858.5 divided by 550. So this value becomes 3.38 kilojoule per degree Celsius. So this is the value that you'll have. Okay, so now let's put this value in this particular expression. So we will get the delta S gas as, if you look at the integral, so you'll get mg into cpg. This will become natural log, and this would be Tg2 upon Tg1. Alright, now because it's a heat that is lost, this entropy change has to be a negative value. Okay, so you'll just see how the negative value would be achieved. So this complete value is given to us as 3.38 into natural log. Now Tg2 is how much? 550 degrees Celsius, and Tg1 is 1100 degrees Celsius. So the Kelvin equivalent is 823 for 550, and for 1100 it is 1373. So when you find this value, so this log is a value which is less than 1, so it will be a negative value. Okay, so it comes about 1.725 kilojoule per Kelvin. And let's go, so this is delta S gas. So if you look at the delta S water, it was 3.77. So the total entropy change, would be delta S water plus delta S gas. So this is 3.77 minus 1.725. So this gives you a value of 2.045 kilojoule per Kelvin. So this is basically the entropy change of the whole system or of the whole universe. That is a combination of water and gases. Okay, so the increase in the unavailable energy, this becomes equal to T0 into delta S total. So this is T0 is 30 degrees Celsius, so it becomes 303 into 2.045, and this would be in kilojoules. So the value becomes 620 kilojoules. So this is how you have to attempt this question. So this question was a question on the entropy change due to a finite heat transfer, or you can say heat transfer through a finite temperature difference that is always irreversible in nature. So the concept that we studied in the video of irreversible heat transfer through a finite temperature difference would be applied over here, and the increase in the unavailable energy concept in the formula would also be applicable. So this is how you would be solving this question. I hope you understood it. Now let's move on to question number 2.